Hey everybody. So in the last couple of videos, we looked at graphs for sine and cosine, and I've got those graphs here, cosine in blue and sine in red. And I'm going to use these two graphs to investigate the the graph of tangent. The sine of tangent isn't something we're interested in right now. So we're going to use the graphs of sine and cosine to do this because I want to remind us of this relationship. The tangent, one way to define it is as the quotient of sine over the quotient of sine and cosine, sine of x over cosine of x is equal to the tangent of x. So what this means, I'm going to look at the values of sine and cosine based on this graph. I'm going to do this intuitively. You can always plug values in and see what's happening, but I want to get us kind of thinking about how this works and see what we get. So the first thing to notice is that if tangent is the quotient of sine and cosine, that whenever cosine is 0, tangent is not defined. Right, so I'm going to try to draw a vertical line. I'll just copy and paste this. Whoops. Oops, sorry. Let's just move this down a little. All right, here we go. So we've got a 0 here. And then I can copy and paste. There's a 0 of cosine here. Come on, there we go. A 0 of cosine. All right, I'm just drawing the ones that are visible here. Obviously, this graph goes on forever. So you'd be able to do this. We could keep doing this on and on and on. I'll just put in one more. So these are the places the graph. Oops. Oh, geez. Let me just undo that. There we go. The graph of tangent cannot pass through these lines because these are the lines where the cosine is equal to 0. And so it must not be defined. Tangent must not be defined. So let's do another couple things. Let's look at the zeros. Tangent will be 0 whenever sine is 0, as long as cosine is not 0 at the same time, but they're never 0 at the same time. So we can look for the zeros of sine, and I see a 0 here, a 0 here, a 0 here. Sine is red, a 0 here, and a 0 here. Okay. So we know that the tangent graph has to pass through those zeros, right? So those 5 points I have there, and then obviously extending forever as these graphs go on and on, but the ones on our screen, there's 5 points that tangent must go through. So I'm going to look at the graph of tangent around the y-axis, okay? So right now I'm going to look between the y-axis and this first blue line that represents where tangent can't exist. And let's put in the values. This first 0 for cosine is at x equals pi over 2. This other one is at x equals negative pi over 2. That you can just get from the unit circle. So let's think about what happens. Tangent, so again, I'm looking between 0 and pi over 2. Tangent is the quotient of sine over cosine. Between 0 and pi over 2, both of them are positive. So I know it can only spit out positive values. The numerator, represented by this series of red dots, is increasing, right? The denominator is decreasing. So if you take a fraction and you increase the numerator while decreasing the denominator, you're making it larger, right? If you go back to first learning fractions, you often learn it as like dividing pies up or something like that. 6 divided by 3 is 2. You have 6 pies divided by 3 people, everyone gets 2. Well, increasing the numerator is increasing the number of pi's you have, so everyone gets more. Decreasing the denominator is decreasing the number of people you have to split it up among, so everybody gets more. So our function tangent must be increasing in this area, in this region between 0 and pi over 2. Even more extraordinary, what happens as the denominator of a fraction gets really close to 0, right? As we get really close to pi over 2, sine is basically 1. It's changing from like 0.9, 0.99, things like that, while cosine is getting incredibly growing incredibly small, very close to 0. When you make the denominator of a fraction very, very small, something interesting happens. We can see this quickly. Let's just look at a simpler version of this just to get an idea of what's going to happen. If you look at x and 1 over x, okay? So I'm looking at what happens when I make the denominator of something very small. So in this little toy example, x is our denominator. If x is 1, this is just 1. If I make x 1/10, the reciprocal of this is 10. It's gotten 10 times bigger just by getting that about 1 unit closer to 0, right? I'm making the x values smaller. Let's make x a little smaller, like 1 over 100. So right now, the distance, as we move from here to here, we're starting out a distance of 1/10 of a unit from 0 and moving to a distance of 1/100th. We haven't even moved a full 1/10 of a unit, but let's look at what happens to the value we output. The reciprocal of 1 over 100 is 100. And now we're less than 1/100th away from 0. If we move even closer, now we're 1/1000th away. The output is 1000. So we're moving very small distances. 1/100th is not very small, our distance to 0, but we haven't even covered that entire distance. We're 1/1000th short. Meanwhile, right, so the distance here is less than 1/10. The distance here that we're moving is less than 100th. So we're changing our input by less than 1/10 and less than 100th, but we're changing our output plus 90, plus 900. So the output is changing much faster, okay? In other words, this thing rockets off towards infinity. We can keep playing this game. 1 over 1 billion will spit 1 billion out. And there's no limit to how small we can make x, and there's no limit to how big we can make 1 over x. The same thing happens here. As this cosine gets very, very close to 0, right? As we get closer and closer to this point right here, where the cosine, the denominator is 0, the output values are rocketing off because sine isn't doing much. And the only thing it is doing is increasing, so it's only helping that rocket off towards infinity. And so what ends up happening is the tangent graph has an asymptote here, where it's shooting off towards infinity. Meanwhile, we can play the exact same game between 0 and negative pi over 2. Everything over here is the same, except that the cosine values are negative and the sine values are positive, right? The blue line, sorry, I reversed that. The sine values are negative. Notice the red graph is below the x-axis and the y-axis is above it. So one of them is positive, one of them negative. So we get the same numbers spitting out, but they're now negative. And so this graph looks like this. And what happens, this shape repeats because we'll keep seeing the same relationship between the numerator and the denominator. One of the only difference is which one's negative and which one's positive. And in the end, we end up with something that looks like this. This repeating graph with asymptotes, one going to positive infinity, one going to negative infinity. We'll look at a much nicer graph in just a second. Oops, I missed my asymptote here. It looks like I went over it, but I think we get the idea. And this graph keeps repeating. It's periodic, just like sine and cosine were, but now the period's a little smaller, remember the period of sine and cosine is 2 pi. The period here is just pi. Okay, and it has to do with, well, let's look at a unit circle. Here's one way to interpret why that's happening. So here is our unit circle. So we know that the definition of the tangent is if we draw an angle we look at where it hits the unit circle, and the tangent is going to be the y coordinate over the x coordinate. Well, what happens if instead of this angle, we add an extra pi? Remember, pi is an extra half turn. So this new angle I've drawn that goes all the way around down to here, the symmetry of this situation, I think is easy enough to see that this point down here is going to have the same coordinates as our original point, except now they're both negative. But if you take their quotient, you've got two negatives, you end up with tangent of negative y over negative x is just equal to tangent of y over x. So with sines and cosines, you have to get all the way back to where you started to repeat because you're getting negatives where you once had positives. But now, because we get these negatives canceling out, we get we repeat a little more quickly. One other way to think about it, I mentioned that the tangent can also be thought of the slope of the line that the angle makes with the origin, right? So, or this ray from here to here is part of a line, the tangent is the slope. Well, this is just the other side of that line. It's going to have the same slope. So for any angle you make, let's make a new one here, like over here, there's another angle in this direction, just a pi rotation difference that has the same slope, and it will have the same tangent. So we get this repeat every pi instead of every 2 pi. All right, let's look at a nicer picture of this. Let's look at, here's a nice graph of sines and cosines. And if we throw in tangent, there's that picture I drew. Let me back out a little bit. I'll get rid of the sine and cosine in just a minute. Let me point out a couple of things. Notice where cosine is 0, we appear to have an asymptote. I can't draw it perfectly. And where sine is 0, tangent is hitting 0. So that red graph, wherever the red graph is 0, the green graph is going to be 0 as well. Okay, let's look, let's get rid of sine and cosine. Oops. All right, and so there's our tangent repeating forever and ever and ever. Now it just looks like a green wall, but we get this, this nice repeating asymptotes as it shoots off to positive and negative infinity. All right, let's do a similar thing with cosecant and secant. What we should expect, I'll put the secant graph up, or cosecant graph up in a second. Here's the graph of sine. Cosecant is 1 over sine. What should we expect? Well, wherever sine is 1, cosecant should also be 1, because 1 over 1 is 1. Wherever sine is negative 1, cosecant should also be negative 1, because 1 over negative 1 is negative 1. So we expect these points, I'll just do the 2 near the origin, to be the same, but we should hit all those the same points repeating in both directions. Wherever sine is 0, we should expect cosecant to not exist, because you can't divide by 0. 1 over 0 is not defined. So in these 3 spots plus every repeating, right, sine is equal to 0, and every pi, every multiple of pi, We expect cosecant not to exist. And we expect something similar that we saw with tangent. As sine gets very, 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 very small, cosecant should get very, very, very large because we're taking the reciprocal. So let's take a look at this graph. Right, and we see exactly what I was mentioning. We hit these, we're hitting all these points where, let's erase those. We're hitting all these points where sine is 1 or -1 and cosecant will be the same. Where sine is 0, cosecant has asymptotes. It shoots off to plus or minus infinity. Let's just look at it without the sign. It's this odd shape that where sine is always between -1 and 1, cosecant's range is on the outside of that, right? And we see a similar thing with cosine and secant. As we'd expect, they're the same shape, just shifted. So the same relationships hold with sine and cosecant, right? We see the exact same relationships, just shifted. So here's what cosine looks like. And then tangent, let's look at cotangent. We could play the same game we played with tangent, looking at the quotient of sine and cosine, except now it's cosine in the numerator, sine in the denominator. So you get a very similar shape, but it's flipped. And the zeros come where cosine is 0, and the asymptotes come where sine is 0. So it's similar shape, but it's flipped and shifted just a bit. Tangent is the one of these that we will use the most, but it's important to know about the other ones as well. So let's just finish up with a quick summary. It's just important to remember that y equals tangent of x. Its domain, it's going to be all x such that sine of x is not, cosine of x. Cosine of x is not equal to 0. Where is this? This is, so another way we could write this is x is not equal to, well, it's pi over 2 plus any multiple of pi times an integer. Right, so if you think about our unit circle again, where is cosine 0? Cosine is 0 whenever the x coordinates on this unit circle is 0 at those angles. And that's going to happen. The first time it happens that we usually think about is when we have an angle pointing straight up, right? An angle of pi over 2. If I add pi to this, I get an angle pointing straight down. If I add pi again, I get an angle pointing straight up, and I can keep adding pi, or I can subtract pi because -1 pi, if I start at pi over 2 and -1, I'm down here, and then minus another one. So any multiple of pi, integer multiple of pi, all the positive and negative integers, added to pi over 2 will get us at a point where cosine of x is 0. So those are the x values we have to throw away. The range is going to be all real numbers. Remember the graph of tangent, right? If I draw one little period, it went off to positive and negative infinity at these two asymptotes. So we can find inputs to get any possible output. Let's do cotangent. The domain, it's going to be all x such that sine of x is not equal to 0, or x is not equal to any multiple of pi, right? A similar reason, just looking a little bit differently, right? Sine if I'm starting with the 0 angle right here, that's where sine is 0. If I add pi, I'm looking at this angle. I can keep adding pi or subtracting pi anywhere along that x-axis. So no integer multiples of pi for cotangent of x, and its range, just like tangent, is going to be all real numbers. And then let's continue with secant of x. This is the reciprocal of cosine, and so its domain is going to be where cosine is not equal to 0, so the same as tangent. So all x not equal, let's be a little clearer, all x except x not equal to pi over 2 plus an integer multiple of pi. The range, we can write this a couple ways. I'll write it this way. It's -infinity to -1. Remember, it was below the cosine graph. Or we can use this union symbol for or, 1 or higher. And then finally, y equals cosecant of x. We'll see a similar thing, a domain, all x, except where x is equal to an integer multiple of pi, and the range is going to be the same, -infinity to 1, -1, or 1 to infinity. So we can hit all the values we want on the output except those in between 1 and -1. Okay, that's it for this video. Just to get a basic glimpse at what these graphs look like. Thanks, everybody. I will see you in the next one.